Okay. All right. All right, so let's see. I think, well, I don't know, people can't see. I don't know if they need to see me. Nobody needs to see me. So we're gonna start in just a second. Right. Good. That's not what we want. And on session 3. All right, so let's talk, guys. What do you think? Any
I'm having trouble formalizing, like I understand 1.3, but I'm having trouble putting it as a formalized.
okay, let's take a look. So it's, you said problem 1.3.
Yeah,
This
Yeah.
is,
that's not of the abuse. I can probably figure it out.
well, we can take a look at it for sure. Still on here. Okay, 1.3. So 1.3 is saying this guy here. We have the natural numbers. We know we have the set 1 to, okay, even Arden says it wrong. Horrible. It should have 0, but okay. And he has a shift map, S, sending natural numbers to itself, which just adds 1. He wants to prove that it has no right inverse, but it has infinitely many left inverses. Okay. So let's let me just do myself a favor and copy this. Okay. So, well, what do you guys think? So,
What I count on is that, like, you can do the left inverse would be, like, whatever, the left inverse is 2 minus 1.
okay.
That's not valid for n equals 1, because I didn't know if that's what I can like manipulate that to get the fact that it doesn't, it's not defined for 1 that doesn't have a right inverse.
Okay, so let's look at what it would mean to have a right inverse. All right, let's address this. Prove that S has no right inverse first, and then we'll deal with the second part. Okay, so for S to have right inverse, we need a function T. I'll call it T, sending natural numbers to itself, for which S composed with T is equal to the identity. The identity function, right? It sends everything exactly to itself. So now functions have these things like ranges. You learn about range of a function, right? So the range is the set of all of the things that this guy, that your function is, hidden, going to. And what you can see here, the identity is going to have the range, which is the entire set, right? Because everything gets sent to itself. But if I compose something on the right, the range of this guy is going to be contained in the range of S, right? Because it's S of T of whatever. Right? So if we look at the range of the shift function S, what is the range of the shift function S? 2 to infinity, right? So the range of, well, maybe, yeah, I'll say this parenthetically. But this is where my intuition is coming from. So I'm just trying to share that part. So the range of S is this, which is not everything, right? In particular, we're missing 1. Which means that which means that this can't happen, right? Because, but now if we weren't, so that's my intuition, but now, now let's prove it kind of formally. I'll just say it, more. This is intuition. And the formal proof, I'll just say by contradiction. So suppose such an S exists, or such a T, sorry, such a function T exists. Then then S of T of 2, or sorry, 1, pardon me, 1. Well, this equals 1 is equal to this, right? Because this is this identity, which is equal to T of 1 plus 1. But then T of 1 is 0 by subtracting, right? Which is not defined. It's not in the natural numbers according to our. So this is not defined. This is a contradiction. It's a contradiction. Because we have T is landing in natural numbers, and we've got T1 is not in the natural. So therefore, no such T exists. Okay. So that would be a proof by contradiction, simple, kind of straightforward. Now, on the other hand, what about left inverse? Okay, so you guys tell so now, on the other hand, well, give me a left inverse. So let's call it R or something. Well, maybe L for left. Let L. Okay. So what is a left inverse going to do? Well, S shifts everything up by 1. So L has to shift everything down by 1. But there's one number that it can kind of do whatever it wants with, right? Because L has to take everything that has been shifted and take it down. But there's one number in the natural numbers that hasn't been shifted, that in the image of T, in the image of S has not been shifted, right? Which is 1. So L can kind of do what it wants with 1. And so let's actually define several L's. So let's let L, so I'll just say this. On the other hand, for any n in the natural numbers, let L sub n be a function. We'll define it this way. Be defined by, well, ln of m is going to equal one of two things. It's equal m minus 1 if m is greater than 1. And it's going to equal n if m is equal to 1. And then you can check, and I won't write this, but if you're writing this down for the homework, please do actually do the check. Check that it is a left inverse for all. So there are infinitely many, of course, right? Okay, is that good? Does that make you feel pleasant?
I'm having a hard time formulating.
Yeah, sometimes, so these types of proofs and problems, I would say, you know, it's helpful to have this kind of feeling like I can define things, I can define functions with a case kind of definition. That's one thing that I think, you know, can help. And then the proof by contradiction is kind of a nice thing, but you know, when not everybody is really that adept at proofs yet. So if you kind of share your intuition and kind of convince me through that, then I generally give full credit. I mean, I'm not looking for, I just want a sound logical argument. So I'm with. Okay, other thoughts, other questions?
For 2.4, especially on A, when we're looking at if the general linear group of complex numbers contains the general linear group of real numbers, well, you have to go through the axioms, but what will be the axiom for the operation? You know, for nothing, I mean, whatever you do for composition. What would be the composition for axiom 2 or 3, whatever? No,
So you're checking, well, so all of these are going to be subsets, yes?
yes.
So H is going to be a subset of G here,
Yes.
right? So you don't have, and it's a subset and the operation is going to be the same, right? You're always using the same operation. If you're going to answer a question like this, to say that something's a subgroup of another thing, it means that when you look at the larger group, the operation of the larger group tells you how to operate, what the law of composition is of the smaller.
So you say
set.
that for any operation you could apply to the general linear group? Or because like when you look at like real numbers, they find it under multiplication.
Yes, so here this is multiplication and H is a subset, but they're asking you to show that this is a subgroup using this operation, the larger group's operation.
Yes.
You don't define any new operation on the sub.
But what would be the operation for that subgroup on general linear?
It's the same, it's matrix multiplication.
Oh, so it's always gonna be multiplication.
For GLN, general linear group, it's always multiplication. That's what they're referring to. Addition doesn't actually work.
Yeah.
If I take two invertible matrices and I add them together, I don't necessarily get an invertible matrix. For example, take the identity and it's negative. Those are both invertible, but when you sum them up, you get 0.
Okay.
So it's not closed under addition. Is that okay?
Mhm.
Right? Good. That's it.
I point,
Um,
sorry, yeah.
I was gonna ask about like, well, a quick question about 4.9 and then I have no idea how to approach 4.10.
Okay.
But with 4.9, I tried to like give logic for why there are that many things without listing every single one.
Okay.
Because I didn't want to list every single object.
Sure, okay.
Is that how we're supposed to try to do it? Or should I have just listed every single element of S4?
S4 is a sort of special group for the symmetric group. S2, S1, S2, S3, and S4. Well, S1 is silly, but all of these are like actually pretty special. Once you get to S5, things start getting kind of more uniform and normal, more standard, and that has actually to do with that quintic business. But so yeah, the general you can certainly do it. So well, maybe I should ask though, what was your argument? I mean, what is your, so like I want to say yeah, it'd be fine to do that, but it's as long as it's a good argument.
So like anything of order 2 is gonna have to be taking elements and just flipping them back and forth.
But you can also have the disjoint.
And
the
so-
disjoint ones.
And so you've got to find how many are just taking 2 elements and switching them back and forth, and then count how many are taking like both sets of 2 and switching it back.
Yeah, let's talk about this. So that's good. That's actually correct. No problem there.
It's dirty.
It's not dirty. It's going to be very clean.
'Cause
So
isn't the order the least common, I mean, of that thing, the least common multiple of the lengths of the separate loops?
That is correct, actually, yeah. So if you take a permutation will have a unique up to up to switching the order of the cycles, it will have a unique disjoint cycle decomposition. So you can always write a permutation as a product of disjoint cycles, more or less uniquely, up to kind of, as I said, changing the order of those disjoint cycles. So if you, and what you just said is true, right? If you want to find the order of that element, namely that minimal number for which when you take that element to that power, you get the identity, it is going to be the least common multiple of those cycle orders. And that's because each of those cycles has order equal to its length. And so you can kind of have to have some number that each of those numbers divides. And just take the smallest. So the question you're asking is, so how many cycles, well, how many permutations, I should say, are there? Type ij and ij, say KL. Right. Well, the first case is if you've taken two, I don't remember, no, 5, 10, 10, right? That's just,
Yeah.
Okay. If you've taken 5, 10, this problem should be easier than if you haven't taken 5, 10.
Use generating functions.
That's a little excessive. That's a little, sure, they appear in generating functions, but I'm thinking even more elementary. I mean, what are you really, if I want to look at the number of transpositions, yeah, you need to pick two elements. This ij is the same as ji as a transposition. They're the same. So you're looking for how many two element subsets are there of a subset of size n in general, but in this case 4.
Yeah, I just did the thing from pre-algebra where you go like 4C2.
Okay, and yeah, you can write this or you can write 4C2. They're the same. This is just different notations for the same thing. And this is equal to 6. Good. So if you want the formula, right, this is 4 factorial over 2 factorial times 2 factorial. The number, incidentally, of transpositions in Sn is n choose 2. So, and that would just be n factorial over n minus 2 factorial. Well, we'll just write it this way, 2 factorial times n minus 2 factorial, or if you want, n times n minus 1 over 2. Okay, so 4 times 3 over 2 is 6. So there's 6 of these guys. And now we can look at the case where have 4 elements is very, very special and very nice, very easy. Because if I determine this, then I've automatically determined the other one. So I can count how many there are by just saying, well, for each one of these, I'm going to get a unique guy over here. But
There's 3.
for each one of the transpositions, I will specify a unique other transposition, is what I'm saying. That will give me one of these guys. However, for each of those transpositions, or for each of those permutations I get, I will have counted twice if I go through all possible transpositions. Right? So how many then do I get here?
3.
Yes, I get 6 divided by 2. So I get 3. It's like overcounted by twice. 3 possible. So the total number is 9. So it's not too hard. I mean, it is, if you do this in like higher dimensions. Or higher dimensions, higher numbers of at higher n, then it can get a little more cumbersome, but it's, you know, it's still pretty standard. It's still not, it's a combinatorial exercise.
Okay, so we can just like, for the third one, we don't need to like do the whole inclusion, actually, we just said that if we fix it, there's two others.
You can say for each, yeah, for each permutation, I get a unique, for each transposition, I get a unique permutation, each of which comes from two transpositions. So that's 6 divided by.
So now how do we gloriously face 4.10 of a finite set?
Yeah.
Doesn't technically
Yeah.
produce
I have no
it
idea.
doesn't produce technically a finite set.
Show by example that the product of elements of finite order in a group need not have finite order. That's great.
Does a finite generate in
If the group is abelian. Okay, so now, all right, so good. So product of elements. I think that, yeah, so, huh? How does what? I thought they give an example in the book here for SL2Z or something. I think they probably do.
I have not seen.
Okay, then, well,
But it still helps to watch through it. Just
My book
Yeah,
is
yeah.
on my laptop, and my laptop is missing an action at the moment.
huh?
My laptop is missing an action, that's what my book is, sadly.
Uh-huh, I see. Yeah, I mean, I think that, I'm trying to think of like the simplest example. I mean, of course, you can easily, you know, give a, well, you can do something with the basic generators and relations and, you know, produce one, but maybe let me think of SL2. I think SL2Z or just GL2R or something you should be able to get an example.
Wait, can I feel like there's an easy proof that it has to have a finite order.
It
but
doesn't.
I mean, it doesn't, but I feel like if we have an element in this group that has the finite order,
Yeah,
and there's some generator X, then that each element has to be X to some power. And so a product of those elements would just be X plus MN or something like that, and it would still be
wait, so say what your argument is.
like, if we have an element in here, the
Uh-huh.
element can be represented as X to some power with X, if X is the generator.
An element to that's in here, we can represent as X to some power.
Is this a cyclic group if it has a finite order?
Okay, let's understand the question first. Show by example that the product of elements of finite order, which means I'm taking this to mean that you can find elements of finite order in the group. What does that mean? What it
Let the
means-
A be finite, but like
Now, the group is not finite. The group is not finite. Okay, if the group is finite, everything is finite. So there's two different notions of order. There's the order of the group as a whole, and then there's an order of an element. An element, the order of an element is the minimal natural number for which when you take it to that power, you get the identity. So it's sort of the order of the cyclic group generated by that element. That's the order of an element. So he's saying, find some elements in a big group that have finite order, so that when you take their product, you get something of infinite order.
Oh, that should be pretty easy.
Because like, in here,
Because,
because like, quaternion.
He does, they do quaternions?
Yeah, does that sound right? Is that what?
I mean, I don't know, is that, tell me what the example is. I mean, I would look in the book, but yeah.
Says H is the set of plus or minus one, plus or minus I, plus or minus J, and plus or minus K.
Yeah, I know what the quaternions are, but what is the example?
At least to a form, I don't know.
I think I got one.
Give the example, I don't know.
I mean, I would try, there's like S and T from SL2, although I feel like these are simple generators. So let me just have to remember. Big one minus one.
I've got one.
Yeah.
So the one you showed us in class for that rotational group with 3, we could take, what we could do is taking the group of complex numbers as our group, or taking all the complex numbers.
Yeah.
You could have like -1/2 plus √3 over 2i, and then your other number would be just i.
This is not going to work. So this is not true if it's an abelian group, and complex numbers and multiplication is an abelian group. So in the abelian setting, and this is part of the problem, he's saying, what if the group is abelian? If the group is abelian, then this will be finite order. If I take product elements of finite order, that we can show. We'll show that in a second. So right now I'm thinking, so you want to think non-abelian. There's a hint for everyone at home. So, and I'm thinking maybe we'll experiment here for a minute. Oops, sorry, I'm going to copy that problem.
Are we looking for matrices? Is that what?
Hmm?
That would be a non-abelian thing.
Yes, we're looking for matrices. I'm thinking, as I said, I'm thinking GL2. In fact, I'm thinking SL2. I believe SL2 has 2. You can generate it by an order 4 and order 3 element. I think I've got to remember the.
What's SL? Wait, I'm forgetting.
Yeah. So these are matrices with determinant 1.
Oh,
I believe this is the case, but it's been I haven't thought about it in a while. So. So let's see, although what it is I well, unhappy with the idea of it though. Be honest. Yeah, I'm gonna have to think for a second here, guys. You guys think too. And let me see. I mean, I know some super kind of silly thing that I can say to you, but I don't want to say that. So I'm trying to come up with something more concrete. This is the point. Maybe this is what I can do. Yes, maybe this is what I can do. So I'm thinking 1 minus 1 or 1 1 minus 1. This is not an SL2. But it does satisfy this nice good, it's not orthogonal. Okay, so this is, let's call this something X. This is in GL2. Or Z if you want. We could even do Z. Now let's see here. Let's try this one. Somehow I don't like it very much. No, I see. Okay, hold on a second. And I'm not a huge fan of this one, to be honest. It is, they're both fine in order, but I don't think I like it very much. So I don't want to do this one. Let's kill it. On something a little simpler. Maybe the other one worked, but let's see. What am I thinking? This is silly. I think I can just do this, can't I? So this equal y. I can do that. Okay, so let's just check. X squared, what is x squared? Identity, good. Finite order. So finite order again, it means I can take that thing to a power and get the identity. What is y squared? Identity. Both are finite order. Now, what is yx? 1, 1, 0, 1. Should look a little familiar. I think we had a problem in the first exercise that looked even more complicated than this. But if I take this and call this z, if I take z squared, you'll see that this is equal to 1, 2, 1, 0. And in fact, if I take z to the n, you can see this is going to equal 1n, 0, 1. Which is not going to ever be the identity. This has infinite order. And if you're wondering, how did you come up with that, Dr. Kerr? The answer is, I have a lot of experience with mathematics and with groups. So I knew this existed. And in fact, I think there's a much more famous version of something like this, which I'm just not. So I had some confidence that I could find something like this. So.
I like that. I feel like the thought process that went into making that was very simple.
Now, so this is a product of elements of finite order. 2 elements of finite order gives me something of infinite order. Okay.
Oh, it doesn't have order in terms of the group.
Yeah, it's elements of finite order.
Yeah.
Elements. That's it.
what
That's
was causing me those problems.
I think I was just having vocabulary issue
Yeah,
problems.
I like read the part of the textbook, but I couldn't quite like suss out what the like one line they gave to defining that quite.
yes. So lesson here. Order. There's order of the group, capital G, and then there's order of G. 2 different notions. So this is just the number of elements in the group as a whole. This is equal to the number of elements in the subgroup generated by G, the cyclic subgroup.
Oh, so we consider it as a cycle.
So yeah, I mean, if you look at X and you look at what do you get in the cyclic subgroup of X, you get X and identity. X squared is identity, and that's all you have. By the theorem we had today, if you have a generator, you find that minimal number where you get the identity, you know, that minimal number is the order of that cyclic group.
Okay.
So this is sort of the smallest number. When I take it to that power, I get the identity.
And so the difference between that subgroup and if G was a cyclic group is that like, I can't say it.
So now let's look at the other case. Let's look at this abelian case. So abelian, and this is one of these things. Abelian groups are way easier than non-abelian groups. Like if you have some abelian group that's generated by a certain number of elements, you know, you can classify it completely. Non-abelian groups, there is a classification theorem. It's complicated, and it was only in my lifetime that they actually finished it. It was a long project that, and I don't know why we did it. Not me, but why mathematicians did it. It's a weird. I'm not in love with the ideas of it. Anyway, there's some interesting stuff, but okay. Anyway, moving on. So suppose G is abelian, and you guys can tell me what's going on. So suppose G is abelian. And let's say G1, G2, all the way up to G sub K, these are a finite order. And we'll give the actual orders, say orders N1, N2, up to NK. So again, this means, parenthetically, this means, well, it means more than this, but this implies that Gi to the Ni is equal to our identity. So it means that, it implies that, but it also means that ni is the smallest integer for which that is true. Smallest positive.
The smallest open vectors to a power, you get like, you do the first two, that's the identity, and the identity, if you keep apples playing with the same thing, it'll just continue to do that. Why are we here with the smallest?
Well, that's the definition of order. For this problem, we actually don't really care about that part of the definition. So sometimes the smallest part sometimes is important information because it will give you the size of that cyclic group. And so if you want to, measure that, it's helpful to know that the order talks about that size. But for this problem, it doesn't matter so much. We just need to find some integer, some positive integer that does this job. So. Like -1 to the 10th power is 1, but the order of -1 is in the multiplicative group is 2, right? It's the smallest one. Okay. So now let's take the product of these. Let's look at G1 times G to the K. Just take the product of all of them. I want to say that I can raise this to some positive integer and get the identity. But what positive integers, does anything come to mind?
You take all the ends and multiply them together.
Yeah.
Let's go.
Yeah, because here, see, here's what I want you guys to do. I want you to be really uncomfortable for the first time, maybe for the first time in your lives, using the rules that you're used to using for arithmetic. I mean, I can't tell you how many mistakes I've seen grading so far of people just commuting, taking an inverse of a product and bringing that inverse in without anti-commuting, right? There are delicate things that you have to be really careful with now that we don't have commutativity. So I want people to develop a keen sense of, I shouldn't do this unless I really feel like I'm sure that things are okay. However, when we have an abelian group, meaning it's commutative, right? Meaning the operation is commutative, then we don't care. Then we can apply our usual rules. And indeed, in this case, because we can commute everything and gather the GIs together, this is going to equal G1 to this power, G2 to the power, all the way to GK to this power, N1 to NK, right? And this is because of abelian. Because G is abelian. Again, it's sort of like, it's the difference between having $5 in your pocket and being, a billionaire, as far as like the level that gap is the difference of like complexity of an abelian group to a non-abelian group. Okay, like there is a huge difference of complexity. This small little thing really makes a huge difference. And so we can do things when we're abelian that would be unthinkable in the non-abelian setting. So, but here we can apply our nice rules. We get G1 to the N1 to some power, namely K, G2 to the N2 to some power, and 1 and 3, GK to the N1, NK, excuse me, to the N1 up to NK minus 1.
Wouldn't that equal 1 or the identity?
I'm just spelling it out. Yep, it does, right? And so the whole point is that because we know that these are the orders of each of these respective elements, we do know that each of these is the identity some power, which of course is the identity. So this is just 1 times 1, which is 1. So when you have an abelian group, life is good. Better?
Yes.
There'll never be an abelian group in which they're finite with the order of the difference and
Well, there are abelian groups that are infinite that every element is finite order. There are such things. And if you want an example, you can think of, you can look at the unit circle. So here's an example of what we're talking about. So if you look at the unit circle, we know this is a group. So this is inside of C star, it's a subgroup. Now, of course, this is not, well, I don't know if of course, but it's not, maybe not obvious to you, or maybe it's not. This is not, there are elements of infinite order in this group. So this, maybe call this S1. However, you can take sort of the elements that are in some sense rational. In other words, you can take inside of here, you can take an even smaller subgroup, which is the set of all roots of unity. They're all the elements that if you take them to some power, you'll get the identity. So all things that satisfy some equation that looks like this, where n can be any positive integer. This actually forms a group. It's infinite.
Because there's infinite spots around the circle.
Yeah, it's actually dense. Whoa. It's dense topologically, meaning its closure is the entire circle. So it's just, there's a, you know, it's like rational points on the real line. And so it's this huge set. Every element, you can take some power, you'll get the identity, but it's infinite. So there are groups like that. And in fact, this is a book, a group that's actually, I think it's called the Pontryagin group. This has a name. And it's actually quite useful in homological algebra. It's very useful to play. So. Anyway. Lots of math. Yeah.
Wait, you said it's dense on the circle, these roots of unity?
Yeah.
So like every single point in the circle?
Yeah. Well, dense means that if I take its closure in the sense of topology, if I take the smallest closed set that contains all these points, it will be the entire circle. Another way of saying it is if I look at any point on the circle and I take any little epsilon neighborhood of it, it will contain points in this set.
But what if we had like the point 1 over pi radians around the circle?
1 over pi.
Yeah.
So you're saying you want some point here. Where do you want the point?
Like at
Here.
1 over pi radians around the circle.
I don't know what to say with 1 over
If
pi.
it's dense and it's closed, right, and therefore it's the
Dense sets are not closed. Dense sets are just dense. Dense. So what is, this is a totally different class. So sorry, everyone at home. You can fast forward through this part. But the idea is, if you're not watching live, I guess, the idea is, so, okay, so let's just stick with subsets of some Euclidean space. So we say, actually, let's just say it this way. Let's say that set, I don't know what to call it, D contained, I don't like D very much, but okay. In, what to say here? I can't say anything. I want to say things, but I can't. I want to say I've got a topological space, but I don't want to say that. So let me say, we say that D contained in S1, let's just be very clear on this particular case, is dense if for any element, let's say P in S1, and any real number, epsilon, greater than 0. There is a Q in D such that when I look at the distance between P and Q, if you want, you can maybe take the displacement vector. I'm thinking of these as vectors. Maybe do this if you're more PQ, take the displacement vector. this is less than epsilon. In other words, there's some element Q whose distance is less than epsilon for every real number. I can make that as small as I possibly want, 1/1 billionth of, whatever. And it's, yeah.
I guess.
Yeah,
so it's just
whatever.
like epsilon delta.
This is, I mean, well, there's no delta in this one. This is simpler than that. I would say. This is just saying that epsilon is used frequently in whenever you're dealing with topology, just to represent an arbitrarily small,
Since
positive
right
number.
above 0, but it's 0.
You want to think of this, just make it as small as you want. You can always get something. So
I think I wrote out my root in a way that is mathematical and should make sense. Like, I can't imagine that is a root of unity.
it's not a root of unity. I'm not saying the root is roots of unity.
It's one of these dense points, isn't it?
No, it's not a root of unity. So denseness, I'm not saying, let's take a look at the definition. I'm not saying that this P is in this set. I'm saying it's close, very close, like I can find something very close to P. Think of it as rationals and reals. That's the most classical thing. Where the rationals are dense in the reals. You can always, which says you can always approximate any real number by a rational to arbitrary orders of, of precision.
So dense doesn't mean we would like, in the number line, dense doesn't mean we have every single real number.
Not at all. In fact, you have a very small, tiny measure 0 set of it. But you have almost nothing of it. But you can get close.
So it's just if you have, say, some big set M, if you have some subset A, if the closure of A is equal to M, it's dense, essentially, or?
Yes. It's saying, so if you're comfortable with closures, this is precisely what it's saying. It's saying that closure is equal to the M set. That's topology. Totally not needed. Don't study this for this class. And I wrote that purposely so it would disappear. Okay, good.
Now everyone's
Don't study that. Please ignore that. All right, is everyone happy? Oh, other question? Anything else?
5.1, I don't know if it's just because we just talked about it today.
Okay, yeah, probably. I didn't get all the way through a lot of this. But
I don't really know how to start. Just because it's new and I need to go read through it.
yeah, this one I think you want to read through a couple of times. So here's a hint. So hint. I'll write it on here. So if G is cyclic, then G is equal by definition, just it has a generator, a single generator. Okay. So what is phi of X? What is this? What is this? So in other words, you can take that generator, use your homomorphism and send that generator some element of G prime. What is the subgroup generated by that? And I think your answer will be, it has to be everything. But then it's a cyclic group. You found a single generator of G prime.
Oh, yeah.
So there's a hint. This is not, yeah. Don't write this as your answer.
Great.
Oh, and then like the next part follows pretty closely from that then.
Yep.
Okay.
Yeah. Well, actually, I think the next part is a distinct statement. It's not, so you're not assuming that G is a cyclic abelian group. You're just assuming it's abelian. So the next part you want to take on its own, but it shouldn't be too hard. It shouldn't be too hard. Okay. Okay, guys. Well, that concludes problem session part 3. And we will